So hello everyone, today we'll be discussing about nested learning, a completely new paradigm for continual learning, uncovering the hidden learnings in deep learning architectures. It was published by Ali Behrouz and his fellow mates from Google Research. For those who don't know me, I am Isaac and I am a graduate student and a researcher from Northeastern University. So let's begin with this NeurIPS poster that was presented in San Diego this year. Um, so Ali went through his research talking about the illusion of deep learning architectures and how they have developed this new architecture called Hope to improve the learning of large language models or transformer architectures over a large number of tokens or given inputs. So we will be discussing a lot about the basic knowledge of deep learning optimizations, weights, and how they are interrelating the optimization problem with deep learning architectures or multiple layer perceptrons, and then overall how they are conveying that um, the new architecture performs much better than GPT-4 or Llama models for various tasks. So to begin with, in order to understand this paper, we will have to understand what momentum is, momentum, memory, and a bunch of other optimization algorithms, so that we can uh, move on to this paper. So I'll begin with some basic introduction to gradient descent. So gradient descent is nothing but a an optimization algorithm, a basic optimization algorithm that helps um, improving the weights of learning algorithms such as multiple layer perceptron, or even in linear regression ML algorithms. They use gradient descents to reduce the mean square error values so that it can reach the optimal values, and the model is mostly generalizable for various given tasks. So this gradient descent has a certain thing called momentum, which is used by optimizers to uh, improve the rate at which we reach the local minimum point. uh, Gradient descent is nothing but a parabolic equation where let's say this is the start of the learning process. It makes sure there's an incremental step, initial weight, it reaches the global minimum point with the most minimal cost, and to make sure this there is an incremental step, we have several different optimizers that help us reach this global minimum point. And one of them is the Adam optimizer that is quite popular for various tasks. So as it's mentioned here, gradient descent refers to a minimization optimization algorithm, follows a negative gradient downhill of target function to locate the minimum of the function, and it is basically a first order optimization algorithm, and this explicitly makes use of the first order derivative of the target objective function. So in order to uh, make sure we get the new weights are basically calculated based on the old weights, and there's an alpha value which is known as the learning rate parameter, and multiplied with the derivative of loss with respect to the previous weight. So this is basically how the weights are calculated. The new weights are calculated from using the gradient descent algorithm. So there's a bunch of uh, optimizers that we could understand, and these are um, adaptive optimization. It's called AdaGrad, RMS Prop, and ADAM optimizers. So I will not go into depths of these optimizers, but these are some optimizers that are widely used, and ADAM optimizer is the most uh, uh, used right now because it usually performs better than the other optimizer. So when it comes to adaptive gradient optimizers or AdaGrad, there is a term called cache where we use the old cache to add on to the derivative of loss, the whole square, which is added on to the calculation of the new weight. And then when it comes to adder delta, the adder delta is basically an extension of this previous AdaGrad optimizers, which tends to remove the decaying learning rate problem instead of accumulating all the previous squared gradients. But adder delta limits the window of accumulated past gradients to fix some size W. And then there is RMS prop, where there is a small difference in the caching strategy. And then there is ADAM. ADAM is adaptive momentum estimation. There is a term called momentum that is involved in calculating the new weights, and this point of this momentum term is mostly the key and vital part of developing this new research from the Google research team. And I also learned about this thing called L2 regression loss, which it adds a penalizing term, mean square error loss, and helps shrink the model coefficient weights towards zero. And it does not shrink it to exactly zero, but it shrinks it towards zero, reducing the model complexity and preventing overfitting. So it basically helps prevent overfitting when it comes to um, a mean square error scenario. Comes to L1 regression loss, there is a good chance that it makes it exactly zero, which helps us perform automatic feature selection. But L2 regression is more used in terms where we have good correlation between features. And if you guys are not really aware of what I'm talking about right now, I think it's the best time to brush up a bunch of machine learning fundamentals and then come back to this video. So after the way that Ali had explained about this paper during the NeurIPS poster presentation was, so there are two different types of learning, context learning and uh, perceptual learning that happens, that comes from the pre-training, where the model already learns and keeps it as a long term, and context-based learning, which helps learn at the moment or the active present. But the problem comes when the model tries to transfer this particular memory, the short-term memory, to the long-term memory. So for example, uh, when a model is not able to transfer this particular memory, the short-term memory, to a long-term memory, it is very similar to a condition that humans have. And this condition where humans face anterograde amnesia. So anterograde amnesia is a condition in humans where they tend to have a good clarity of the memory that is already there in the past, but or in the long term, but when it comes to short term, they tend to have a lot of understanding about the present for a certain number of time and they forget it. So similar things are going on with LLMs, where they are trying to get the active context, but they are tending to forget it in the long term, which is giving a lot of hallucinations and making the learning of LLMs a black box, or unable to solve that problem. So this nested learning paper mainly brings out how different layers or architectures within the large language models learn, and how we can optimize it to the maximum so that we can make sure the model keeps learning over a continual period of time, or for a very long period of time. So to begin, different types of frequencies that in which the brain works. So there is delta waves, theta waves, alpha, gamma, and beta waves. So they use this particular uh, neurological study in order to map the architecture that they uh, created in order to uh, uh, like map them in order to get an accurate representation of how a transformer could work. So there are linear inputs given V, K, and Q, which is a bunch of uh, inputs, and then it's basically mapped uh, with the values, and it is passed through a frequency bunch of high frequency neurons, uh, and then mid frequency neurons, low frequency neurons. And why they are called high frequency, mid frequency, and low frequency is based on their updation from time to time. So these high frequency neurons are the ones that get updated quite frequently, whereas low frequency neurons, as they go by, are much less active and like much less updated. So they wanted to make sure to understand how the learning happens between all the neurons so that they can optimize the algorithms that work in between them, and make sure they are uh, learning for a long time. So here is previous research that showed them that stacking multiple layers done in deep learning models only improve the expressive power in representing complex features, but it increases more internal computations or flops, all of which are very critical and desirable characteristics, but um, it's not a universal solution when it comes to like learning over a long time. So this is just a bunch of backup information that they have. And when we come up to nested learning, so nested learning has um, nested learning was developed with the foundation of associative memory, and this is a new paradigm that they are proposing, that the entire learning process happens as a key value pair kind of an objective, where they basically say that, let's say the model learns by looking at a certain face, this is this person, and if it looks as another face, and that is another person, and so on, we are able to uh, say that uh, the entire set of learning happens through key values, right? So we aim to first um, so associative memory is the ability to form and retrieve connections between events. It's a fundamental mental process and is inseparable common component of human learning. And as you can see, RNNs, they work on a bunch of attention mechanisms, which is something that you would uh, learn in in this paper called "Attention is All You Need" in attention mechanism. This is the basic transformer architecture. In order to uh, explain this, you will have like a bunch of inputs which goes through an embedding which is basically converted into embeddings along with positional encoding, where you determine the position of each word in the input, and then it is passed into an attention layer where they will determine how much attention you will give for each word in that particular sentence. You'll pass them to a feed-forward neural network, add normalizations, which is there in every single layer, and then comes the decoding layer, where you'll again pass through mask multi-head attention, and then multi-head attention, and then feed forward, and you'll get the next predicted word or an. So our goal is to redefine the learning based on momentum for now. So we have discussed about momentum and the different learning optimization algorithms, being Adam, Erasmus Prop, and so on. But Adam is basically the algorithm that uses weights. We are going to try to understand how we can use the backpropagation process to map the particular values or inputs uh, as key value pairs. So let's say we understand that we get the new set of weights. So we are going to uh, say that one can use this particular formulation and reformulate the backpropagation process as the solution to an optimization problem on finding an optimal associative memory. So we are going to try to backpropagate the entire associative memory that the large language model holds. For example, the key value pairs. So when an LLM learns that a given input has one key and one other value, and let's say for suppose it might be wrong, or it might be like incorrect. When we are trying to find the optimal values, we are trying to backpropagate such that we are able to understand the mapping itself better. So the entire learning is in terms of keys and values. So this is the entire formulation that they had come up with in order to show that the backpropagation can also be done, saying that they had discussed about weights and this term called momentum. So this momentum term was uh, inspired from Adam Optimizer, and this momentum term uses learning rate. The momentum also acts the weight is an optimization problem, as well as the momentum term helps in also understanding the learnings in the uh, large language model or a transformer architecture. This momentum term, they are using alpha 1. So alpha I plus momentum minus learning rate derivative of loss with respect to the given input and weights. So mi is the momentum at state I, and alpha I and eta I are the adaptive learning rate and momentum rates respectively. So given that we are able to say that uh, we can use this particular formulation to understand, to basically map the entire uh, learning in neural networks. Uh, and for a more expressive association, they have made sure they have added this value, the value term, in that particular equation that we have previously discussed, and it is resulting in an equation where there is a change in the momentum formulation. It also considers the value term, and it also helps in updating the weights. So overall it is all being interconnected and becomes a part of a nested learning uh, paradigm. So this is what they have discussed in this paper, and the next step in order to make it even more better, they have introduced the L2 regression loss, which we have discussed uh, before we started this uh, paper. So in L2 regression loss, we tend to minimize the errors by uh, um, like reduce the loss as much as possible by using a penalty term. So they have also introduced that particular thing here in order to derive their own uh, uh, yeah, in order to derive their own optimization problem, which is the L2 regression loss. They have made sure they have to consider another problem here, that is bringing in nonlinear um, yeah nonlinear outputs. So nonlinearity, I think this is a typo error, but let's say they are trying to bring in the nonlinearity into this particular problem, and they are using uh, the Newton-Schulz method, which helps up with this optimization problem, and they are using it in a new architecture as well that they had proposed, which is the Hope architecture, and it contains a self-referential learning model, or yeah, it basically contains a self-referential learning model, or the Titan module that was introduced in one of Ali's previous research. So the existing architectural backbones consist of the working memory module or attention, but um, actively fuse and is responsible for actively fusing information across sequence length of equal neural network, updated over limited context window, and so on. So they're trying to bring the continuum memory system, which is formalized as so and so, and how they are like using the MLP blocks. So this is the same thing as we discussed earlier, and somehow they were able to uh, pull off some really good results. Perplexity versus context usage, the level of hallucinations in the Hope architecture with DGD, delta gradient descent, and then continual momentum, and the Hope architecture in general, and how the perplexity is reducing, whereas when it comes to transformers and titans and combo architectures, it's much larger. And then there is another benchmark that they had discussed. Yeah, this one, you're right here. So when it comes to the task of continual translation of novel language task, uh, they discussed about Llama 3 plus RAG, GPT-4, GPT-4o mini, Llama 8 billion parameter model, and different architectures such as Hope, ARMT and Titans and RMT and so on. And they were able to absolutely nail the accuracy when it comes to performing this particular task, whereas you can see models like Llama 3 and GPT-4 like struggled a lot. But yeah, like over the time, like RMT and such architectures are pretty much the same when it comes to large number of tokens, like let's say 10 million set of tokens, and memory levels, and yeah Hope architectures, while retraining uh, those models, they basically use the base models and then built the architecture on top of it. So yeah, this is a bunch of information on how different mm, uh, different modules within the deep learning architecture can be interrelated, and uh, basically uncovering the illusion of learnings within the deep learning architecture. Although this seems like a major breakthrough, this is still being studied, and of course, they have cited one of the greatest quotes: "We cannot solve our problems with the same thinking we used to have when we created them." So, this is a completely new level of understanding how deep learning algorithms work in the background, and to know a little more, I think, yeah. So this is where the nested paper was originally introducing nested learning, a new paradigm for continual learning. So yeah, Ali Behrouz is a student researcher, and he is from Cornell University. As we discussed about anterograde amnesia and so on, yeah, mentioned here, and this paper was published at the New Reef 2025, um, and a lot, yeah, same thing that we discussed, and mapping keys and value pairs, high frequency neurons, mid frequency and low frequency neurons, deep optimizers using L2 regression laws, and then continuum memory systems, and finally the HOP architecture, and how uh, the HOP architecture like performed quite better than simple transformer, Samba, and Titan models that were produced. Um, yeah, pretty much it. I think we discussed a lot in this video, and I look forward to seeing you all in the next video. Hopefully, discussing on some groundbreaking research from institutes across the world. I am looking forward to cover more image model. Thank you for watching this video. If you want to learn more about the latest advancements, subscribe to this YouTube channel. I look forward to seeing you all in the next one.